Section 8.1, Radical Expressions. We'll start with the basic idea of a square root. We say that b is a square root of a if b squared is equal to a. So, for example, the square roots of 100 are 10 and negative 10, because 10 squared is 100, and negative 10 when squared is also 100. So therefore the square roots of 100 are 10 and negative 10. Now in symbols we say that the square root of 100 is 10. So when we see this symbol, we understand this to mean the principal square root. So this is the principal or the positive square root of 100 in this case. So now in this next exercise in symbols, we have the principal square root of 100, which is 10, and then we have the negative to the left of it, so that would change the sign, and that would give us negative 10. Alright, so then here's a couple more. In symbols, how would that evaluate? So this says the principal square root of 9, and so that is 3, because 3 times 3 is 9. And then in symbols, the square root of 9 is 3, and changing its sign, this will give you negative 3. For us to be good at evaluating square roots, we have to know the perfect squares. So what I mean by that is this 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, and 15 squared is 225. You should probably commit these to memory, as they will be very useful in helping you identify perfect squares and then also knowing how to go from the square to its square root if necessary. Alright, I'd like for you to pause and try the first 3 examples on this page on your own. The principal square root of 49 is 7. The principal square root of 36 is 6. The square root of 121 is 11, changing its sign, negative 11. Now the next exercise asks us to determine the square root of 4/25. So, what number squared gives 4? And that would be 2. What number squared gives 25? And that would be 5. So the square root of 4/25 would be 2/5. If you wanted to check your work on this, 2/5 times 2/5 is 2 times 2 over 5 times 5. 4 over 25. Let's try the next one on your own. Determine the square root of 1/16. Well, the square root of 1 is 1, the square root of 16 is 4, the square root of 1/16 is 1/4. Now the next one's a little trickier. Square root of 0.81. Now we see 81 and we notice that's a perfect square, and so we might guess something to do with 9, and that would be correct. The answer is 0.9. And you can check this in one of 2 ways. You could simply multiply out the decimal number. 0.9 squared is 81, and we need 2 decimal places, 0.81. You could also think of this as a fraction. 0.81 is 81 over 100. So the square root of 0.81 would be the square root of 81 over 100. 81 squares is square root is 9. 100 square root is 10. 9 over 10, which is 0.9. All right, try the next one on your own. Determine the square root of 0.64. The square root of 0.64 is 0.8. And you could check this in several different methods as shown in the previous exercise. Evaluate the square root of 93. Well, 93 is not on our list of perfect squares. So in fact, its square root is more difficult to find. Now we might guess that the square root of 93 is between 9 and 10. And that's a reasonable guess, because 9 squares is 81, and 10 squares is 100. 93, since 93 falls between 81 and 100, its square root would fall between 9 and 10. Turns out that the square root of 93 is approximately 9.643 6507 6099 2955. Now, I didn't do that in my head. I had a calculator handy, and I found this using the calculator. But what I would like for you to notice here is that this decimal part doesn't end. It also does not repeat. And if you remember anything back from like chapter 1, when we have a decimal number that does not end or does not repeat, we would say that the square root of 93 is irrational. We can write it exactly using the symbols as shown. The square root of 93, that's exact. We can approximate it using a calculator. If you have a calculator handy, approximate to 3 decimal places the square root of 156. All right, so on my calculator, I found that the square root of 156 was 12.4899. So if I were to round up, right, 0.489, that would round up to be approximately 12.490 to 3 decimal places. And again, this is an irrational number. The square root of 156 is irrational. 156 is not a perfect square. Now, what if we had the square root of negative 25? Can we evaluate this square root? Well, is it 5? All right, could it be 5? Well, nope, can't be 5. 5 squared is 25, which is not negative 25. All right, so what about negative 5? Well, that won't work either, because negative 5 squared is also positive 25. Well, what about 5 times negative 5? Can we do that? Well, that's not a perfect square. You're not multiplying the same number by itself. So what's the square root of negative 25? Well, it turns out that at this time, we cannot determine what the square root of negative 25 is. So what we will say is the square root of negative 25 is not a real number. And in fact, in general, the square root of a negative number is not real. All right, so here we have a few numbers, and we're going to try to identify each of the numbers as one or more of the following. Is it a real number, a rational number, an irrational number, or none? Okay, so let's see, the square root of 28. Well, 28 is not a perfect square, so we know that it's irrational. 28 is positive, it's real, so this would be real. The square root of 28 is a real number, but it would be irrational. 144 is a perfect square. In fact, the square root of 144 is exactly 12. So therefore, the square root of 144 is real, and it is rational. 12, and then the number stops. It's an integer. All integers are rational numbers. The square root of negative 1 is not real, so it cannot be rational or irrational either. So we would answer to this none. The square root of negative 1 is not real. So to guide us into a couple of applications of square roots, let's introduce the Pythagorean Theorem. If you've never seen it before, the Pythagorean Theorem tells us that in a right triangle, now if you aren't sure about what that means, a right triangle is a triangle containing a right, which is a 90-degree angle. And so we can see in this diagram we have a right angle. That's what that little square in the one vertex signifies. In a right triangle with legs measuring A and B and hypotenuse measuring C, A squared plus B squared will always be equal to C squared. Now, the A and B are interchangeable, but C is always the side opposite the right angle. And C will always be the longest side in the triangle. All right, so let's see how we can use this. A right triangle has legs A and B with hypotenuse C. Find the exact length of the missing side. All right, so if A is 8 feet and B is 8 feet, then what is C, right? That's what's missing. All right, well, using the Pythagorean theorem, since we have A squared plus B squared must be equal to C squared, then 8 squared plus 6 squared must be equal to C squared. 64 plus 36 must be equal to C squared. 64 plus 36 is 100. So now when we have a situation like this where we have a number square equal C squared equals a number, we can write that C must be the square root of the 100. And so C would be 10 feet. All right, why don't you pause and try this one out on your own. Find the exact length where A is equal to 8 meters and C is equal to 17 meters. Applying the Pythagorean theorem, we would have 8 squared plus, oh wait, now in this one, the B is the unknown. B squared equals 17 squared. So then 64 plus B squared equals 17 squared. Now we didn't do this one on our sheet, so let me multiply that out real quick. That would be 49, carrying a 4, 11, 0. That would be 289. All right, now this one's a little bit different. We have the B squared on the left, but we have this other constant associated with it. Let's subtract the 64 from both sides. And then B squared would equal 225. So then B would equal the square root of 225, which is 15 meters. The lengths of the sides of a triangle are 5 feet, 10 feet, and 12 feet. Is it a right triangle? Explain. Why don't you try this one out on your own? If it is a right triangle, it must satisfy the Pythagorean theorem. So which one would be the A, the B, and the C? Well, remember, if it is a right triangle, this would have to be C. The hypotenuse, it is the longest measure. So then we would need to satisfy 5 squared plus 10 squared. Is this equal to 12 squared? 5 squared is 25, 10 squared is 100, 12 squared is 144, and 125 is not equal to 144. So we would have to answer, is it a right triangle? No. The sides do not satisfy the Pythagorean theorem. All right, finishing off with an application. A flat rectangular television has a screen that is 20 inches wide and 16 inches tall. Find the exact length of the diagonal and approximate the length to the nearest tenth of an inch. All right, so basically, if we have a rectangular television, just draw a little rectangle here. All right, and it is 20 inches wide and 16 inches tall. Find the exact length of the diagonal. So now the diagonal refers to that measure, and that's unknown. So now notice in a rectangle we have right angles. So I've got a right triangle here, and I'm missing the hypotenuse, so that's the C. So then I would have 16 squared plus 20 squared is C squared. 16 squared is, let's see, 16 by 16, 36, carrying a 3, 96, 0, 6, 1 is 256. So we have 256 plus 20 squared, that one's easier, 400 is C squared. And so we'd have 456 is C squared. So then C would be the square root of 456. And this would have units of inches. This would be exact. this measure is exact. It is still in its square root form. It does say, though, to approximate the length to the nearest tenth of an inch. So if you have a calculator handy, you can do this. You would find that C is approximately 21.4 inches. And notice how I've used a different type of symbol. This is approximate. I made the squiggly equal sign. That's an approximation.